Welcome back to the next video about my electronic steering wheel jog IP68 project. In the first video we did some measurements of possible forces, at least I'm able to exert on such a steering wheel jog. Card here, link in the description. And so in this video we will do some static calculations to see what it takes to handle these forces. Enjoy! Here's, at least in principle, what I'm talking about. So we have our steering wheel here at the front, and this will be somehow attached to some shaft. And I will probably use 6060 aluminum, so aluminum, mangan, silicium 3.5. And that shaft will run in a POM-C bearing, which needs to be attached somehow to something. Otherwise, I'm just holding that in the hand. And we have probably two more aluminum extensions here, washers, whatever, at the ends of the shaft to hold the whole shaft here inside the POM bearing against any axial forces. And again, that's absolutely not to scale. That's just the principal idea. And of course I have a Lego model for the whole thing. So our black shaft, our two stops on each end, so the shaft actually stays in our green and yellow POM bearing. And we have our wheel. The first question we can ask is how long must the aluminium shaft stick out here for me be able to comfortably grab the wheel, and at the given forces, radial forces, how much deflection of the shaft is acceptable. And we can, in that case, assume that this is a perfect bearing and holding the shaft in here perfectly. I determined the required stick out for our shaft at 70 millimeters, 0.07 meters. And I did that by just grabbing the wheel here, other way around, grabbing the wheel in a quite awkward angle and looking how far my highest knuckle is standing out here. That's one component. Then half of the diameter of the wheel itself plus 20 millimeters reserve. You remember we have to mount the whole stuff somewhere. The outer radius of my steering wheel is 30.5 millimeters. My knuckle height was 37 millimeters, and then plus 20 centimeters buffer for some mounting plate or whatever for the whole contraption, and that gives you 60.5. And if we generously round up all measurements here, so 15, 40, 20, we come through to 65 millimeters, and if we round that up, worst case, we come to 70 millimeters. So our statics model is a shaft that is rigidly fixed here to some unmovable wall or something of a certain length and of a certain diameter, which experiences some force. We already determined the length. That would be our 0.07 meters. And we also need the modulus of elasticity, or the E value of our material. For 6060 aluminum, that's 70,000 megapascal, respectively Newton per square millimeter. 1 megapascal is 1 Newton per square millimeter. Instead of getting into the nifty math and the details and making your own Excel spreadsheet, you can actually use one of the dozens online calculators for bending beams that are out there. This is one I really like, and I put a link in the description. So we have this situation. We have a firm clamping here and our end is free and we have a point load directly at the end. And our length here of our beam, of our shaft, is 0.07 meters, and the force, that's what I measured last time, the maximum radial force on the wheel is about 210 newtons, and the force is acting here at 0.07 meters, exactly at the end. And if we go further down, we can, select the profile of our shaft, which is a perfect circle and a diameter. I start at 20 millimeters and the material is aluminum and the E value is 70,000 newtons per square millimeter. I already showed you that. And then we get a nice deflection curve here, which stops at before 0.05 millimeters. We could, in theory, make our shaft diameter a little bit smaller. It's really not necessary to have 0.5 hundredths of a millimeter deflection. We could accept more deflection. So let me use that calculator and come up with some table. I told you we would not go into the math, but we should have at least a quick squeeze at the formulas governing the whole thing here, so we can understand the results here a little bit better. So, delta, our deflection, is equal to, the formula is out of a book, okay, P, that's the force, our 210 newtons, times L cubed over 3 times our modulus of elasticity, E, times I. And I is the moment of inertia. And the moment of inertia for our circular beam here is equal to pi times d, the diameter, to the power of 4 divided by 64. And what you should take away from all of that is that our deflection here increases with the cube of the length and it decreases with the 4th power of our diameter. And here are the results I got from that little web app. So I made 15 calculations for 3 different lengths of our beam, from 0.07 meters down to 0.05 meters, and 5 different diameters of our beam, from 20 millimeters to 12 millimeters. And you see in this direction here, as we decrease the diameter, the numbers are increasing, according to that law, to the power of 4. And if we make the whole thing shorter, the deflection decreases with cube, following a cube law. But the important thing here is in that range here, between 20 and 60 to 60 millimeters and maximum length and 2 centimeters shorter, the deflections are all below 1/10 of a millimeter, which is not noticeable when you're hanging on the wheel with 20 kilos or 21 kilos or more. And even if we make the whole thing even thinner, down to 12 millimeters, our deflections are all below a millimeter. So we're fine there, I guess. As I told you, that was the easy part. Now let's see what's going on inside of our bearing and with our shaft inside the bearing. If you go to a website of a reputable bearing vendor, you usually get a whole lot of documentation. I think the longest I've seen was a 50-page PDF with lots of drawing and math and stuff telling you how to calculate bearing loads. But these are all assuming that you have a radial load at the center of your bearing, which we don't have. So we have to improvise a little bit here. So let's make a cutaway model of our bearing. And here it is. We're assuming for now as a worst case that the bearing is supporting our shaft only at the very ends. So when I apply some force here, I have 2 points of contact, this one and this one. Now let's make some static calculations. We can model the whole thing simply as a lever with a fulcrum. So that part is our stick out and there's our outside force, 210 newtons. That's the length S for stick out, and that's the length of our shaft inside the bearing, B. And we have a force at the back of the bearing pressing down, cancelling out that force. And then we have a force at the front of the bearing. And calculating these two forces is really trivial. That's really just your typical lever thing. So our force at the back has to cancel out exactly the momentum. Our force here at the front is imparting on our lever, and the moment imparted is of course the force times the length here, so S times F, and that's back, that's a momentum, back converted to a force. We have to divide by that lever length B here, and we get the force in the back. The force here at the front is simply the addition of these both forces to cancel them out. So F front is equal to F back plus F, and F back is S times F over B, and then plus the F. And if we just draw the F out, we get here F front equals F times, in brackets, 1 plus S over B. Just to show you the magic of static calculations, especially that it doesn't matter where you put your point of rotation in a lever. Let's have a look at this setup here. So our fulcrum is now here at the back, and here we have our front force, and here we have our external force, still the stick out S, and still the length in our bearing B. So the front force is impairing a moment here with a lever B plus S of F times B plus S. And to calculate that back in a force here with a lever of the length B, we divide that by B, and we do some transformations here, and we get to F times, in brackets, 1 plus S over B, which is of course exactly the same as above. And the back force here has to cancel out our two other forces, so F back is equal to F front minus F. So we take our F front here again, so that's equal to F times, in brackets, 1 plus S over B minus F, and we arrange that a little bit, and we come again to our S times F over B. The important point here is that our force here at the front of the bearing is always greater than the force at the back. So that's the important force to have a look at. And that force has in its term S over B. So it gets smaller the longer we make our bearing. Now, I did a bit of Excel this time so I could show you some nice curves. So we have here 3 different curves for 3 different stick outs. We used these stick outs before, so 5 centimeters, 6 centimeters, 7 centimeters. Below here on the x-axis is our bearing length between 5 centimeters and 15 centimeters. And here is our force at the front. And yeah, the radial load is still 210 newtons. Let's first have a look at these 3 points here, where the stick out is equal the bearing length. And at those points, our front force is 420 newtons. So exactly the double of our radial force on the stick out. And that's because if S divided by B is 1, if both are equal, then our front force is exactly 1 plus 1, double our radial force on the stick out. And right to that, as the bearing gets longer, the force, of course, increases, 1 over B, but with diminishing returns, okay? This won't never go below the 210 newtons of radial force on the stick out. It will approach at some point 0 if our stick out gets infinite, our bearing length gets infinite long, but diminishing return. While below this point we have not quite an exponential, but an over linear increase of the force. You see here, if we go, for example, for the 7 centimeter stick out, from a bearing length from 7 centimeters to 5 centimeters, we increase the load from 420 to 500 newtons, or a little over 500 newtons. So we learned that the force in the front of the bearing is always greater than at the back of the bearing, and that we can reduce both forces with diminishing returns by increasing the length of the bearing. But that was just some statics calculations. Now, the bearing has also a dynamic behavior, meaning it bends. And if you look here closely, you see when I apply my radial force here at the stick out, that the end somehow complies to my bearing, while we have at the front just a contact point. So greater force and a contact point. That will bite us into the behind later on. But let's have a closer look at how our shaft is bending. Looking at that as a bending beam again, you would model it as follows. So B is the length of our bearing again, and as our stick out, here we have the force at the end, and the total length of our beam would be L equal B plus S. And then we have 2 bearings modeling our bearing, a fixed bearing and a movable bearing. And the distance between the bearings is, of course, the length of our bearing. Too many bearings, I'm sorry. And usually that distance is not denoted B, but A. And we're back on my preferred beam bending site. I already linked it in the description. So now we have the case that bearing A here is a fixed bearing and bearing B is a movable bearing, as I've shown you. And otherwise that picture here is wrong, but fortunately the right picture is somewhere down here. So bearing A, bearing B, movable, and the distance between the 2 bearings is A, and the total length here of our beam where the force is applied at the end is L, as I've shown you in my hand drawing. And I already entered some data for our calculation. So the total length of our shaft is 0.21 meters, 21 centimeters. The distance between the bearings, so the distance of our bearing is 14 centimeters, so stick out of 7 centimeters. And our force is, of course, 210 newtons. And then the whole thing spits out for a circular shaft, 12 millimeter diameter, made from aluminum, that bending curve. And the first thing you noticed is this is an enormous bending compared to what we just calculated for the 7 centimeter stick out in the beginning. I mean, that's half a millimeter bending here. Wow, why is that? Remember, I told you the bending is proportional to the length of the beam cubed. So double the beam length, 8 times the bending, and 3 times the beam length, 27 times the bending. So yeah. But it's not that bad, because this diagram is a little bit misleading. Because here at 0 is the end of our bearing, and the back of our bearing, and here at 14, come on, is the front of our bearing. And now we have a problem, at least with that diagram, because our bearing, if drawn as a straight line, would go from here to here. So the bending inside the bearing is much less, and we have to try to model that somehow. Yeah, I told you that deflection graph is a little bit misleading, because here in blue, that would be our bearing. And if I take the Lego model again here, well, it's not to scale, but you can see again, there is that end here complying to the bearing, and then we have here the point load. And honestly, we could do all the math, but to actually, calculate that distance here from this curve. But let's just go with the maximum deflection here, which should give us at least an order of magnitude of, how our shaft is behaving inside the bearing. Here are the numbers I got out of that little web app for bending beams. So our force at the front of the stick out, radial force, is still 210 newtons, and I did calculations for stick out between 5 centimeters and 7 centimeters, and a bearing length between 5 centimeters and 10 centimeters, which gives us then a total length between 10 and with a maximum stick out of 7 centimeters, 17 centimeters. And we already calculated the force that would be applied here at the front of the bearing. And I further did that for a shaft diameter of 12 millimeters and 14 millimeters, and that's the results I got. The maximum deflection over the whole length of our shaft. And I considered everything below 1/10 of a millimeter as okay, and everything between 0.1 millimeters and below 0.12 millimeters as could work, and everything at 0.12 millimeters and above as unacceptable. Now, this is a little bit too much numbers, so let's have a look at the graphic. Here on the y-axis is my deflection, and here on the x-axis is the length of my bearing, and then we have here the different cases for the different stick outs and the different shaft diameters. And as you can see, these 3 lines here, that's for a shaft diameter of 40 millimeters, which is has considerably lower deflection than the 12 centimeter shafts. And that's not really a surprise, because remember, the deflection is proportional to 1 over the diameter to the power of 4. So a small change in diameter of our shaft will reduce the reflection enormously. And here I made a little mistake because I written down the deflection only to 1/100th of a millimeter. So these curves are a little bit crooked, but I think these two curves show you the general trend here quite good. The other ones, that's just rounding errors. It should always look something like that. The reason being that the deflection is also proportional to the total length of our shaft cubed. And the length is equal to our bearing length plus the stick out, so it's also proportional to our bearing length cubed, respectively to our stick out cubed. But what about the force at the front? That is proportional to the stick out, so the greater the stick out, linear relationship, the greater the force on the front of our bearing. And it's also proportional to 1 over the bearing length. So the longer the bearing, linear relationship, the lower the force is. And now we have a problem. To decrease the force at the front, we have to lengthen our bearing, but as we lengthen our bearing, our deflection increases by the cube. In mathematical terms, we have here a non-linear optimization problem with several variables. And there are no real closed solutions for that. So we have to continue to fiddle around. Calculating a single force here at the front of the bearing is nice and good, but in the real world you really need to know a pressure here. And in our model so far, this was only 1 point or 1 line, and so the pressure in theory would go to infinity, and that's not working. Fortunately, all materials deform under force, and our bearing material also deforms a little bit. So here's a little enhanced model where the bearing can actually deform, and you can see here at the front it deforms very much because the bearing has to comply to the deformation of the shaft, while here at the back the compression or deformation of the bearing is less because there the form of our shaft, the deflection of our shaft, complies to the bearing. Now, to get an idea what's going on at the front of the bearing, we have to look at one other material property of POM. And that's the ball indentation hardness according to ISO 2039 Part 1. So what you do, you take a piece of your material and then you press down on it a little sphere, a ball with a 5mm diameter, until you have a penetration here or deformation of between 0.15 to 0.35 millimeters, not meters, sorry. And then you have the diameter of your indentation here, and then you can calculate from that diameter an area, and then you take the force and divide that by the area, and you get a pressure in megapascal, or that's the same, Newton per square millimeter. And depending on who you believe, POM-C has their value of 140 megapascals, or ball indentation hardness of 140 megapascals. I've also seen values here of 145 and 150. And the thing is, with that test procedure according to ISO, you can have different indentations, and so you calculate the thing, that hardness, for different forces and different areas here. But anyway, it's a good starting point. Now, a shaft of 12 millimeter diameter or larger is not exactly a ball sphere of 5 millimeter diameter, so there is already some safety factor in there. But anyway, I don't want a deformation of a maximum of 0.35 millimeters. I'm aiming more to something like less than 0.1 millimeters. And yeah, the maximum deformation according to that ISO test is 0.35 millimeters. So we have to wiggle that value down by a factor of 0.35 millimeters divided by 0.1 millimeters, 3.5. And so we get a max desired pressure here at the front of our bearing of 140 megapascals divided by that 3.5, and that's 40 megapascals or 40 newtons per square millimeter. It's time to give the elephant in the room and the reason why I'm stumbling about here from calculation to calculation name. And the name the industry has for our little problem, that is putting a lot of load here at the edge of our bushing-like bearing, is edge loading. And the general consensus within the industry is to avoid edge loading or to minimize it as much as possible. And one method we already applied, that is lengthening our bearing here with a bushing inside. But beyond that, you don't get any quantitative information with formulas. Those vendors, bushing vendors, they have very, very long papers with drawings and formulas and everything for calculating the loads of the bearings and how to select the correct bearing for the job. But when it comes to edge loading, the information is very sparse. I have here a document from Schaeffler Technologies, link in the description, which is a little over 100 pages long, and that's here. Not even half a page is about edge loading. And again, avoid it, minimize it, but just some general tips. But there's one thing here which I haven't considered yet. And that's extending your bushing beyond your bearing housing. The idea here is to make your bearing surfaces more compliant to your shaft. I mean, we already know the shaft won't at that point comply to the bearing surface, but maybe we can do it the other way around. In our application, that would mean to extend our POM bearing here beyond the mounting flange and make it a little bit weaker here so it can actually comply to the shaft. And of course, this has a second advantage because our stick out here is reduced. Now we just have to get a feel of how much compliance I need here in the end to get a contact surface that is large enough to keep our pressures below those magical 40 megapascals. This drawing is not very good, but anyway, so we have here our bearing with our new extension reaching out here. And our extension, complying to the shaft. So again, the question is, what's the contact area here? And that's simply the shaft diameter times the length of the contact. And we divide our front force by that area and we get a pressure. I made some more Excel calculations on that for two cases. First, the front load with 360 newtons, that would be a bearing length of 7 centimeters and a stick out of 5 centimeters. And then also for a front load of 385 newtons with a bearing length of 6 centimeters, stick out also 5 centimeters. And then I have here the length of the contact logarithmic. So from 0.05 millimeters up to 2 millimeters, which is a bit much. And then here we have the diameters of different shafts we can use between 12 and 16 millimeters. And yeah, the number here is simply the pressure at our contact surface. So our diameter times our force divided by the diameter times the length. And as you can see, when we go up to 1 millimeter contact length, which is not too much, we are well below our 40 megapascals. And I think that's realistic. I think we should take a break at that point. And yeah, we basically learned a lot. We redesigned our initial design a little bit with that extension here out. And we have a good feeling about the forces here on the shaft and on the bearing, especially on the shaft with the deformation and everything. And I guess in the next video in this series, we will have to talk about how big our pom bearing has to be, and yeah, diameter mainly. Till then, bye.